Hello, everyone. You're all welcome to a Fronius webinar. These webinars are designed to provide information and insight on Fronius products and, of course, on the solutions that we use these products to prefer. So for today, we shall be discussing Fronius string inverters versus string or DC optimized systems. So we shall basically be looking at the economic, safety, and performance factors that makes the use of Fronius string inverter or Fronius-based inverters, Fronius-based system much better or makes more sense than making use of a DC-optimized system. To do this with me today is my colleague, David Mwangi. David is the technical sales advisor for the Eastern Africa region. He is based in Nairobi, Kenya. And then, of course, myself, Cyprian Okolo. I am based in Lagos, Nigeria, and I am the technical sales advisor for the Western Africa region. So together, we shall be taking on this presentation. So let's now have a quick look at the agenda. I'll start off by defining what string inverters are. Have a brief look at the mode of operation, the inception of MLPE. We'll find out what that means eventually. We'll now look at yield losses. David will now come in at this point and continue with shade mitigation, DC optimizers, dynamic peak manager. He will be making comparison between the DC optimizers and the dynamic peak manager. And then, of course, highlight on the disadvantages of DC optimized system. And then afterwards, we'll provide a brief information afterwards. Great. So before we start, please feel free to ask your questions during the webinar by making use of the chat function. Of course, you can see that at the corner pane. Just make use of the chat function and ask your questions. We will, of course, endeavor to answer all these questions during the webinar. And then, of course, we value your opinion. So please give us a feedback, basically regarding the content of the webinars that we provide to you. Thank you. So to start off, what are string inverters? So by definition, string inverters are basically devices, or singularly a device that is connected to a string of solar panels or arrays that converts the energy generated, which is usually DC or direct current, to usable electricity per se at the load point. These usually are alternating current. So we'll have a list here of a product chronology, starting from the Fronius Sunrise, that was manufactured in 1995, all the way to the Fronius Tauro, which is our flagship commercial inverter that was launched in 2021. Among these are some accessories like the Watt Pilot, the Fronius Home Pilot, and the Fronius Energy Cell. This particularly have been not in circulation per se, but apart from these, all these are string inverters that have been manufactured along the line, and we're happy to say that these inverters are still active till today. So, having said so, let's now have a look at what we have today, these days, as a commercial inverter for commercial solutions. So first up is Fronius Simos, or the Simo Advanced, as you will be getting to know soon about them. So we have an outlook of commercial inverters, starting with the Simo, the Echo, and the Fronius Tauro, with their respective specifications, as you can see. Next up is the inverters for our residential solutions. This comprises of the Fronius Primo, the Fronius Primo, the Fronius Simo, the small versions that ranges from 3 to 8.2 kilowatts, And then, of course, we have the big SIMOs or the SIMO Advanced, as earlier said. This can also be applied for residential solutions. Yeah, thanks once again. I've gotten a positive feedback on the audio. Great, so let's continue. Next up is a hybrid inverter. So we also have hybrid inverters to provide battery connectivity, that is battery connectable. So of course, for provision of backup power. So we have the Fronius Primo, single phase, of course, with power classes from 3 to 6 kilowatts, and then the SIMO Gen 24 Plus, power classes from 3 to 10 kilowatts, of course, with all their respective specifications. Good. So having gone through our product list, let's now basically look at that's basically delving into the topic proper. Let's look at the mode of operation. So for all string inverters, they have the modules connected in series. So that means that to get the summation of voltage for a particular string, you now have to add all the operational voltage or the operating voltage of all the modules connected in that particular string. So this means that for this example per se, which has 3 modules in this string, the summation of the total voltage or the total string voltage will be V1 plus V2 plus V3. That is the summation of the operating voltage of all the modules. Great. So also note that in this case, the current passing through the string will remain constant or equal. So therefore, power and voltage increases while current remains the same. This provides for more flexibility. As you can see, different strings can now be connected to our string-based inverter. So, like I said earlier, this provides for more flexibility as it has to do with the installer, meaning that you can continue to add modules in a string so long as you don't go beyond the maximum DC input voltage of the inverter, which basically is about 1000 volts. So why this comes as an advantage and provides more flexibility is that if you compare it with DC-based or DC-coupled systems, the installer usually finds himself restricted in terms of module connection or orientation, because it's restricted to the control voltage of the system, which is usually the control voltage of the battery system. So this could be 24 volts, 12 or 24 volts, or 8 volts. So you wouldn't want to go beyond this control voltage if you're mounting your or connecting your modules to them. So this tends to force the installer to make use of more parallel connections. Okay, so continuing, and of course, let's not digress. Let's still focus on the topic of the day. So now let's ask the question, or to answer the question, what happens if there is shading? So if shading occurs, for example, in this case, we have shade casted upon a module by a tree in this instance. So what happens? So the question is now, okay, does partial shaded module affect the entire string? Well, the simple answer here is no, because for modules, what we have is bypass diodes. So this bypass diodes, as you can see in this case, helps to bypass, like the name implies, shaded parts of a module. So as you can see in this case, the series connection of these microcells in the module has been impeded by this leaf, as you can see here. So this kind of causes an open circuit for this particular shaded or affected area. So, but this doesn't affect the entire module because of this bypass diode. So with this bypass diode, you can at least get up to 66% performance from the module side. But that being said, the shaded module definitely acts like a sort of a bottleneck to the entire string or to the entire system per se, because it will be sort of canceling out the power that was supposed to be generated by the shaded portion. So this is, of course, described with this illustration, showing us the relationship between power, voltage, voltage, current, and resistance. So the voltage basically is the force that pushes the current through a particular electronic system, and then the force at which this current moves, of course, also depends on the amount of resistance that is applied on this particular current path. So let's have a look at the inception of MLPEs. So MLPEs basically stand for module level power electronics. So for module level power electronics, what has really changed that actually has brought us to this stage of the inception of module level power electronics? Well, these are actually emanating from the changing norms and standards from different countries or regions. And where are these standards coming from? They basically well from, I would say, an honest desire to provide as much power from solar source. And then here being the module level shutdown being portrayed as a safe technology. But I would want to ask the question later on, how safe is safe? So we also have a case where module level module level power electronics has also been projected as a safe and reliable solution. So, well, are they? So let's continue and then find out more about the MLPEs. So MLPEs can actually come in the form of DC power optimizers. So what are DC power optimizers? They are basically an electronic device that's connected at the module level to aid maximum power point tracking. It's also a device that is used to implement module level shutdown for regions or countries that has this as normative order. It is usually attached to the module junction box, so basically attached to every single module, and then it gives for a great tolerance towards shading and mismatching. So how about microinverters, which is another form of module level power electronics? So basically, like the name implies, microinverters are inverters that are small in nature, micro as the name implies. These inverters or microinverters convert DC to AC at the module level. So this means that they are connected to the module itself. So it aids MPP tracking at the module level. Of course, it allows for easy expansion of the PV system because of its flexible nature. And then it's also tolerant towards shading and mismatching. That sounds pretty good, right? But then let's take a more closer look into it. So starting with the hard facts, it implies that there will be an extremely high component count of components, of course. There will, of course, be many contact points. For case of roof installation, there will be additional plugs on the roof. There will be increased upfront costs, reduced system reliability due to the high number of components, and then, of course, increased operation and maintenance costs when it comes to OPEX. So let's now have a look at the impact of additional components on service. So we're still looking at the good side of this. We would want to say, okay, well, the more, the better. But then let's recall or have this at the back of our mind, that every electronic component will eventually fail someday. So this is actually buttressed by what we call the bathtub curve. So this depicts the lifetime of every electronic component. So it takes the shape of a bathtub, which is where it got the name. So it actually has 3 stages of failure, or 3 failure stages. So the first failure stage is the early failure stage. We have the static failure stage, which is considerably the longest period in this curve. And then we now have the wear out stage. So for every electronic component, even if it passes through or scales through the early failure stage without any failure or repair, and then does so for the static failure stage, a time will come eventually when it will have to, give way, per se, and will have to be replaced. So that being said, let's now have another come from another perspective with a view of system component view. So assuming we have a system that comprises of a 6 kilowatts system with 20 modules, in order to successfully connect or implement the system, you will need a string inverter. If you're using a string inverter system, of course, you just need one Fronius inverter in this case to implement it. Well, if you're implementing it using the DC-optimized system, you will need one inverter and then 20 optimizers, DC optimizers, because they will have to be connected to every single inverter. I mean, every single module in the system. And then if you're going for a microinverter based systems, you'll basically be needing 20 microinverters that will be connected to all the modules. So, summary, for a string inverter based system, Fronius inverter in this case, you just need one component. For a DC optimized system, you need 21 components. And then for a microinverter based system, you will need 20 components. So, what does more components mean for an installer? Well, as we are analyzing this, let's take note that the lesser the electronics on the roof, the safer the system. This is basically because for every electronic system, they have high temperature coefficient. And for every system that has a high temperature coefficient, there is an utmost need for a cooling system. And given the fact that there is no way we can actually implement a cooling system on a rooftop or roof-mounted installation, per se, this, of course, exposes the system to a risk of fire incidents. So, going forward with the implication of component numbers, let's now look at the impact on service cost. As we were saying, or linked to the previous slide, for Fronius string inverter, you have an average need of just one inverter per 10 kilowatts. But then for MLPEs, you have a need for an average of 30 inverters per 10 kilowatts. So what does this mean? It means that you have 30 times less truck rows or 30 times less maintenance activity or less maintenance cost with regards to Fronius inverters when compared to MLPE-based systems. So, yeah, as I said earlier in the previous slide, what actually brought us to this stage, it's all in the process of mitigating or reducing to the barest system yield losses. So let's now have a look at a closer look at the system yield losses and what actually causes them, and then how it can be, improved upon. So started off with the main causes of yield losses. They are most times design related. These usually come up from common setup and configuration mistakes by the installers, not following recommended procedures in the design manuals per se. Cable sizing, for instance, if cables are not properly calibrated or configured for particular installations, this could, of course, lead to yield losses. Loose connections, we'll have a situation where we have partial contacts. We also have a situation that emanates from irradiation variations, lifetime degradation, and then, of course, shading. So having said that, let's now look at the main causes of shading. We have these can include roof superstructures, which includes chimneys and other extrusions, roof extrusions. We have dots, snow, that is for regions that have snowfalls. Shading can actually be caused by trees, chimneys, as I mentioned earlier, cloud cover, cables, street lights, just to mention a few. So, having said this, let's now look at the effect or the dependency of irradiation, of the module current on irradiation. So, having a look at this IV curve, we can extrapolate and see the effect of irradiation on the module current. So basically speaking, if we're looking at this curve, looking at with regards to the respective irradiation figures for what we have here, 200, 400, 600, 800, and 1000 watts per meter squared, we can see that they have their respective maximum power points. So one unique thing you would notice in this case is that the difference in voltage is quite minimal, per se. So what do we now derive from this curve? The module current is actually directly proportional to the irradiation. So the lower the irradiation, the lower the current. The higher the irradiation, the higher current will be generated by the module. So only minimum changes can be seen at different voltage levels, given with the respective irradiation levels also. So having said this, David will now continue in this case to shed more light on how shade can be mitigated. So David will be continuing from this slide. So David, I'll hand over presentation rights to you now.
All right. Thank you very much, Cyprian, for the first part of the presentation. Now I'll be taking over and look at how to mitigate shade effect on PV yields. So shade mitigation can actually, or shading in this sense, can have a very negative effect on the yield of a PV system. And actually, this is one of the biggest causes of yield losses. And shading can be avoidable in some circumstances. In other circumstances, it is not avoidable. Maybe when you have things like cloud cover and stuff like that. So, but things like trees or chimneys, these are things can be mitigated during the design phase of the system or even during the operational stage of the system. Shading will have an effect on the IV curve, and therefore it becomes very important to monitor the IV curve to detect shading when it happens. And once this shade is then detected, something needs to be done to correct the performance of the DC production. And the possible solutions that we are discussing today regarding DC optimizers, but also to focus more on the integration of an extra MPPT algorithm within the Fronius string inverters, which is the dynamic peak manager, which we will abbreviate here as the DPM. So looking at the dynamic DC optimizers, as mentioned already by Cyprian, these are module level power electronics. And in terms of the configuration, you can have either 1 or 2 modules or even up to 4 modules per optimizer. And in this case, there is a slight advantage in the fact that module level monitoring is possible. So you can be able to tell the power production or the behavior at module level, isolating the module from the entire string. So the DC optimizers, of course, will work by tracking the module peak efficiency. And to do this, they use the normal MPPT technology. Once the efficiency is optimized by the DC optimizer, in this case, then the output is sent to the inverter for AC production. So here also there is a question also of the compatibility between certain inverters and DC optimizers. And therefore, when you have a design that requires you to use a DC optimizer, you also have to look at the compatibility of the DC optimizer with the inverter that you'd like to use in that case. So going further to look at how this configuration might look like, we have an example here. So in this particular typical system with DC optimizers, we see that we have one DC optimizer attached for a module, and then these optimizers are then connected in series, and the power is then connected to the inverter for production of AC power. But the question then begs, what is the effect of such a configuration on the efficiency of the PV array? So we will try to answer that question later on. Before we do that, let's now get into the Fronius Dynamic Peak Manager, just to give you some better understanding of what this entails. So when we look at the normal maximum power point tracking, the basic design of the MPPT is to be able to maximize power extraction from the PV array under all conditions. And therefore, this algorithm, which is MPPT, scans the power voltage diagram and tries to find the optimal operating point. So you can see an example of a power voltage diagram here. So we can see there is one curve during midday that has no shade, but we also have two other curves at 9 a.m. and 8 a.m. that are shaded at two instances. So here we have the generation of two possible maximum power points for the shaded curves. So the biggest problem with the ordinary MPPT technology is that in the case of shading, the tracker often stays at what we refer to as the local maximum power point, as we can see in this curve. So this would be our 9 a.m. curve with a bit of shade. So we have one local maximum power point, and we also have a better operating point, which we refer to as a global maximum power point. And the reason the tracker is getting stuck at this point is because once it tries to shift the operating point, either by reducing or increasing the voltage slightly, then it notices that there is a drop in the power produced, and therefore it stays at this local maximum power point. And therefore, there is therefore a loss in terms of what is possible to be produced even when there is a bit of shading. So with the dynamic peak manager, what is happening is that you actually would end up getting some additional benefits as far as yields are concerned. So you can see in this graph, this would be the shaded part of the production during the day. So these are early morning hours. And therefore, the dynamic peak manager is able to guarantee or to give you an extra 7% more yield from this production only on this green section. But how is this possible with this extra yield? So this is possible because with a dynamic peak manager that is embedded in all Fronius inverters, the inverter is able to scan the entire IV curve. So it doesn't matter whether there is a local maximum power point or another maximum power point somewhere. The entire IV curve is scanned, and the dynamic peak manager is able to find a better operating point, which is the global maximum power point. So therefore, even in the case of shading, the dynamic peak manager is able to operate at a better maximum power point, and this is what is guaranteeing or giving you a better yield of 7% more compared to an inverter that is only using standard or normal MPPT technology. So let's now do a comparison between the dynamic peak manager and a DC optimized system, or what is the performance comparison between the dynamic peak manager and a DC optimizer. So to do this, we have a scenario where we have what you would consider the profit yielding months in some places, which would be April to September, and this would be in unshaded conditions. So as you can see here, we have the specific yield on this scale, which refers to the kilowatt hour generated per kilowatt peak of PV array. And then we have on this scale the period of the year. So we're starting from April, May up to September. In red is the Fronius inverter with the dynamic peak manager, and the gray one represents a DC optimized system. Then the blue curve is our deviation, or how much the Fronius dynamic peak manager is able to produce as a deviation from DC optimized system. So on this scale, we have the extra yield by the Fronius inverter starting from 0.5% up to about 5%. So you can see that over the course of the year, we have the Fronius dynamic peak manager giving you an average of 2.7% more yield. So therefore, even with the additional cost of this module level power electronics like the DC optimizers, which comes with additional capex and also additional opex, you are not guaranteed any better performance. So therefore, at this point, you can see already that there is no value if the normative requirements do not say that you need to install this kind of module level power electronics. It doesn't give you any benefit as far as yield is concerned compared to a Fronius inverter, as an example, with a dynamic peak manager. So we also have another comparison for a 5 kilowatt peak system that is partly shaded. And in this particular example, we can see that we have also quite significant performance in addition of the dynamic peak manager, especially during the period of low irradiation or low yield months. So you can see from November up to around February, the DC optimized system does not perform very well. And one of the reasons is that during low irradiation levels, the DC optimized systems do require quite a bit of power, or they consume quite a bit of power that is generated by the modules, and therefore the reason for this high deviation. So we can see also in partly shaded conditions that the DC optimized system does not offer any advantage, and therefore we can see that we have an even better performance with Fronius manager integrated. Not sure you can hear me. Please confirm if you still can get my audio. I have a bit of an issue here with my headset. Okay, great. Thank you for the feedback. So let's continue and look at the comparison and what has been studied for you to get these findings. So there have been independent tests that have been done regarding the benefit of having these module power level power electronics and systems without this module level electronics. So here we have a study that was done in Denmark, and this involved a PV system with an inclination of about 42 degrees, as we can see in this photo to the right. And these were about 42 modules divided into groups, and different scenarios were tested. So if you'd like to see the entire report, this is also possible. So this was done, as I said, by a third-party institution, and this was by the Associate Professor Dr. W. Toke of Franke, and he looked at the impact of DC optimizers for PV modules, and this was done in the University of South Denmark. So from these findings, what we can be able to tell is that When it comes to the yield, you can see that for a system production during a sunny day with no clouds, a string inverter is able to produce about 18.5 kilowatt hours, whereas a DC optimized system produced only 18.12 kilowatt hours. So therefore, in terms of what that means as far as the entire system is concerned, it means that the DC string inverter system is able to produce 100% of the desired power, but the DC optimized system falls short and is only able to produce about 98% of the desired power. So you can see that we have additional yield with a string inverter system, as we said before, even in the case where you have partial shaded conditions. So let's now look at what are the main disadvantages of these DC optimizers. So there are two main disadvantages of these DC optimizers, and one of them is efficiency, partly covered by Cyprian, and also another one is the failure rate. So when it comes to the efficiency, what you need to understand is the fact that the overall efficiency of a system would be equal to the efficiencies of the connected parts. So in this case, if you are talking about what is the total efficiency of a DC optimized system, we would have to consider what is the efficiency of each of the DC optimizers that is connected to the back of the modules. And therefore, we would go from the efficiency of DC optimizer 1 up to DC optimizer N, depending on how many optimizers are connected in this case. But with a system that is using only the string inverter, then here we would only talk about what is the max efficiency possible from this particular inverter, and therefore the total system efficiency becomes the efficiency of the first component that is in use. And if you, in this case, have only one inverter, then you're talking about that efficiency of the system, overall system, being equal to that of the inverter, which would be roughly about 98%. For a DC optimized system, if you have, for instance, two DC optimizers, then each DC optimizer is operating at an efficiency of about 98%. If you multiply 98% to another 98%, then the overall efficiency actually reduces to 96%. So you can see in this sense that just by the mere fact of having two series connected DC optimizers, you are already degrading the efficiency of the DC output or the power that is connected to the inverter in this case. When it comes to the failure aspect, then this is also another big problem. So about 1 million PV systems were investigated up until 2017, and various types of areas were evaluated. So as you can see, about 47.47% of the causes were actually unknown. We have 26.26%, which were installation errors. Then we had things like electric or lightning strikes that also caused a significant cause of failure, about 15.15%. And then product defects, 9.9%, and error in system design accounted for about 3.3%. When it comes to the error source, we can see that the modules accounted for the biggest source of error with about 36.36%. Then we have the DC disconnector, also a significant source of error with 30.30%. And then the other errors from the inverter itself, the DC connector, and the DC cabling are also accounted accordingly in this pie chart. So when it comes to the problems with DC connectors, or what we refer to as the MC4 plugs, one of the major concerns is the creation of an electric arc. And by physical definition, these arcs are caused by a high potential difference, which would mean the voltage, and high current through an impact ionization. So therefore, this could result to what we refer to as a serial arc, which is quite common, or a parallel arc. So we will see in another slide how this looks like. In addition to that, we could also encounter what we refer to as the electroconductive plasma. So these are high electric field strength, and there is a considerable risk of fire out of this kind of arcs. So anything from about 5,000 to 50,000 degrees Kelvin causes a high risk of fire for any PV system. In terms of how this would look like in a PV installation, we of course are going to speak here specifically about DC arcs, which are quite different from AC arcs. And DC arcs are actually quite constant. So there is no intermittency because the current flow in a DC circuit is quite constant, and therefore the risk of fire from a DC arc is actually a lot higher than even compared to an AC arc, because an AC arc gives you some intermittency between the positive and negative part of the sine wave. So as far as the possibility for arcing is concerned, there is the possibility to get an arc with a voltage of just about 13 volts and a current of 0.4 amperes. But of course, this depends on the type of material that is used. So for 13 volts and 0.4 amps, you could get a significant arc with a copper cable. And of course, like mentioned before, this would have a serious effect also on the UV or IV characteristics. So as you can see here, we have what we refer to as the serial arcs that are happening within the PV array and the connection thereof, and the parallel arcs that are happening near the inverter or the grounding area of the PV system. In terms of the main reasons for electric arcs, so we have looked at all these reasons as we saw in the pie chart, but there are quite a number of things that can cause electric arcs within a PV system. These range from the bypass diodes. It could be a DC disconnector, or what is referred to as commonly as a fireman's switch. If there's a loose connection somewhere there, or when the switch is being activated, then there could be a risk for arcing. DC combiner boxes, it could be related to the modules directly, even in the junction boxes of the modules. It could be screw terminals in the field distributor. It could be general wiring, that is the general installation. Also in the inverter connection area, if the connections are not done properly and following the recommended guidelines as far as even the torque application of the screws is concerned, that could be a potential area for arcing. It could be solder connections in the modules. It could be the DC fuses when, for instance, they break. They could also, if they are not well constructed, they could cause some serious arcing. But the biggest culprit that we have seen and is known so far, these are the DC connectors, or what are commonly referred to as MC4 plugs. So, and to illustrate this further, there is also a study that was conducted, and the general conclusion of this study is that the more the connectors you have in a system, the higher the risk of failure. So, and these failures would result due to corrosion, which could be an influence of the weather. It could be the usage of connectors from different manufacturers, therefore meaning that there is some compatibility issue there. It could be loose plugging of connectors, even when they are from the same manufacturer. Then if they are not properly connected, then you leave some space for arcing due to the loose connections. It could be also something that is due to the bad quality or poor quality of the connectors and the materials that have been used to manufacture these connectors. And then the biggest risk is the danger of mixing up the connectors of different manufacturers. So these photos show us the typical failures. So these are very high risk for fires. So you can imagine if the material around this MC4 plug was easily ignited, then a fire was imminent in this particular failure case. So there is also availability of different studies in the market, depending the causes of fires by the MC4 plugs, and especially when MC4 plugs from different manufacturers are used. So you can see that in this particular lab test, there is the study involving one particular MC4 plug, that is the Stably MC4, that was mixed up with other manufacturers, and this was done around 2013, but the study results are still relevant to date. So we can see from the lowest scale to the highest scale. So the more you intermix from different manufacturers, so here we have from A, B, and C, then the risk of fire as a result increases significantly. So we have start from 75% risk due to the mismatch up to around an additional factor of 330% more, which then would also mean that the risk of fire in this kind of an installation is very, very high. So here what we are saying is that when you have to use MC4 plugs, please make sure that you are using MC4 plugs from the same manufacturer, and make sure that these plugs, because for on-roof or even field installations, the use of MC4 plugs is almost a must. So it's not recommended that you start joining wires the normal way you make wire joints. So therefore, for PV installation, even to offer you security when you have to isolate some modules, MC4 plugs are a must, but please only make use of MC4 plugs from the same manufacturer, and make sure that they are securely connected to each other to minimize the risk of arcing. So in terms of the safety aspect of additional components, so when you have a DC-optimized system, as already mentioned by Cyprian, you have the possibility that you are going to end up with very, very many components that you need to connect together. And the higher the connection points, the higher the risk of failure within such a system. As we can see in this particular example, we have a 6 kilowatt peak PV system that is utilizing approximately 20 modules. And if you consider the use of DC optimizers, as we can see them placed next to each module, then we end up with about 61 connection points or plug connections. But when we use only a standard inverter, like a string inverter, then we end up with only 21 plug connections. So you can see here, the higher number of plug connections definitely at some point would lead to some failure in one point or the other of the system. And therefore, that is something that also must be taken into account. So therefore, this does not only affect the optimizers alone. So if you consider a system with optimizers or even micro inverters, or a combination of a string inverter with other kind of MLPs, you will end up with an extremely high number of additional electronic or electrical components. As already shown with the bathtub curve, at one point or the other, some of these must fail. And therefore, even in terms of the operating costs, starting from the capital expenditure, the more the components you have, the higher the cost of the installation. And in terms of the OPEX also, the higher the number of components that you have, the higher the maintenance costs and so forth. And in terms of the reliability, because of the higher number of components, also there is possibility of failure from time to time, and therefore the overall reliability of this system is reduced. And so with that, we have come to the end of our webinar for today. But before we end, just further information regarding where you can get useful material on Fronius products. So you can go to the Fronius website, the downloads section. If you'd like to watch any of the webinars that have been done before, or how-to videos, these are available in the Fronius YouTube channel. And for the webinars, you have a specific Sub-Sahara playlist. So you can visit this link that is provided here, and you can see all the webinars that have been done for the Sub-Sahara region. For direct contact with any of the Fronius colleagues, if you're in West Africa, please get in touch with Cyprian Okolo. If you're in Southern Africa, Byron Kotze would be your right contact. And in East Africa, feel free to reach out to me. And then for all our international colleagues, if you'd like to contact them, then these are the contact details here. So at this point, we'd like to say a very big thank you for taking your time to join us today for this webinar. We hope you have enjoyed it and gotten a lot of useful content, and do wish you a very good rest of the day. So bye for now.